Hello, calculus fans. Okay, we got a different type of work problem here. We're going to have a water tank in the shape of an inverted hemisphere with radius 8 meters. Okay, inverted hemisphere, what do we mean? Hemisphere, that's half of a sphere. Inverted just means it's upside down. It's filled with water to a height of 6 meters. And what we want to do is find the work needed to pump the water out to a height of 2 meters above the top of the tank. One of the physical properties that we'll need is that the mass density of water is 1,000 kilograms per cubic meter. Now what we'll do is we'll place this tank on a coordinate system. We want the top of the tank to go along the x-axis. Let's take a look at a side view of the tank. Alright, so we've placed the circle so that it's centered at the origin. You can see the water level. That's supposed to be 6 meters above the bottom of the tank. It's filled to a height of 6 meters. Now this is just a side view. This really is a hemispherical tank. If we look down from the top, what we'd see is a circle. So here's the idea. We're going to imagine freezing the water, and then we'll slice the water into thin discs of ice that are parallel to the ground. Then each slice, all the water in that slice, or all the ice, has to be lifted approximately the same distance. So you imagine that you slice this, and when you lift a slice, each water molecule in that slice will get lifted the same distance. That's important because somewhere in our work formula, what do we have? Force times distance. And so in order to measure this accurately, the distance needs to be the same for each, for the slices. Now our slices will be of different heights, and that's where the integral will come into play. Now an equation of this circle is x squared plus y squared equals 64. Remember the radius of the circle was 8. What we want to do is determine the mass of a slice whose y coordinate is specifically at y. Alright, so here's a new picture. This is a little more updated. We look at a slice. So we slice this thing into these thin slices parallel to the ground. And because it's a hemisphere, these slices are going to be circular discs. Notice that the slice that's marked at coordinate y, it has to be lifted 2 minus y units. And the way we can figure that out is because that's just the difference between the y coordinates. We're lifting everything 2 meters above the top of the tank, so that has a coordinate of 2. And then the y coordinate of the slice, well, that's just y. So we have 2 minus y. Notice that y is itself going to be a negative number for those slices. And so that's why that lifting distance is going to be a positive distance. At the bottom there, we see a side view of a slice with a little bit of perspective. We get slices that are circular discs. It has a radius of x because we're measuring a horizontal distance along the slice. It has a thickness of delta y because that is the change in the y coordinate that is measuring from the bottom of the disc to the top. So we've got this disc, radius x, thickness delta y. So since the slice is a thin disc, it's a cylinder, really, of radius x and thickness delta y. Well, that's all we need to know its volume. The volume is pi times the radius squared times the thickness. So in this case, pi x squared delta y. Because we know that x squared plus y squared is equal to 64, we can replace that x squared with 64 minus y squared. So this is our measure of the volume, pi times 64 minus y squared delta y, and this is measured in cubic meters. Now let's go over some of these basic physics formulas that we're going to use. Mass is equal to volume times mass density. Force is equal to mass times acceleration. And work is equal to force times distance. The last two we've talked about already. So let's go step by step to compute the work. Starting with the volume, we know what the volume is. Let's now compute the mass. We're talking about the mass of the slice. So we take the volume, which was pi times 64 minus y squared delta y, and we multiply by the mass density, which was 1,000. And this is mass, so it's measured in kilograms. Now that we know what the mass is, we're going to multiply that by acceleration to get force. This is the force required to lift the slice. So we take the mass, which we had just computed, pi times 64 minus y squared times delta y times 1,000, and we multiply that by the acceleration due to gravity, which is 9.8 meters per second squared. So force is measured in newtons. So finally, we'll compute the work required to lift the slice. So remember that work is equal to force times distance. So we take the force from the previous calculation, which is pi times 64 minus y squared times delta y times 1,000 times 9.8, and now we multiply by our lifting distance. That's the distance required to lift the slice. And work is measured in joules. Now we're not done yet. This is just the work required to lift this one little slice. All right, now we're ready to compute the total work, which we'll calculate by integrating the delta W that we have in the previous calculation. So we just throw everything into our integral. So that's the integral from -8 to 2, and then the integrand is just the delta W expression with the dy instead of a delta y. The limits of integration go from -8 to -2 because those are the levels of the water. The -8 represents the bottom of the tank, -2 represents the top of the tank, 6 units above the base. We multiply everything out, compute an antiderivative, and then we plug everything in, and it works out to this one nice tidy sum, 13,053,600 pi joules. It takes a lot of work to move water around like that, so that's going to be a lot of work that's done. Okay, that's all for now.